So my dear students, welcome back to the session on cables. In this session we are going to study the three-hinged stiffening girders, and this is a very important topic for you from the examination point of view. And I have drawn a three-hinged stiffening girder. The view you can see here. There is stiffening girder here, that is beam. There is another stiffening girder, and then to this stiffening girder there are suspenders attached, and then suspenders are connected to the cable. So this is a typical view of a three-hinged stiffening girder with two girders, and this is the roadway where you can see vehicles or pedestrians can pass. So this is how the stiffening girder looks, and you can see the third hinge here, three hinges. That means two hinges will be here. I will just show the hinges here. One hinge here, another hinge here, third hinge here. Similarly, one hinge will be here, another hinge will be here, and the third hinge. So this is how it looks. The vehicles or the pedestrians can pass through like this. Now this three-hinge stiffening girder will have basically three components, as you can see. The first is girder itself, which has three hinges. You can see this girder or this girder. That is girder nothing but a deep beam, and then a cable with a certain central lip. Then the cable and the girders are connected by closely spaced, what we call them as suspenders. So this is how three-hinged stiffening girder looks. And you should understand that because of the third hinge, again this three-hinged stiffening girder is a statically determinate structure. Now what we will do in this session is we will analyze a three-hinged stiffening girder subjected to some load. For that I have taken a problem. So instead of writing problem here, I have already written the problem, so you all can see. This is the problem that I have taken. I'll just read out. A three-hinged stiffening girder of span 100 meter is subjected to two loads of 10 kilonewton each at distances of 20 meter and 40 meter from the left support. The girder has a supporting cable of central dip 10 meter. So this is the description that is given as far as the three-hinged stiffening girder and the cable is concerned. Then the question that is asked is here: determine bending moment and shear force at 30 meter from the left support of the girder. Also determine maximum tension in the supporting cable. So this is the problem. I hope I will just keep it on the screen again for you to note down. This is the problem. So have you noted down the problem? I hope it is clear to you. Of course, I will be drawing the sketch of the problem, and then we will see how we can solve the entire problem to find out bending moment and shear force at 30 meter from the left support, and then to find maximum tension in the cable. I hope you have noted down the problem. Okay. So now what I will do is I will just take it out. So as far as the problem is concerned, let me draw the sketch of only one girder and cable. That is enough because it is mentioned only one girder. So this is going to be something like this. This is the beam. This is one hinge, another hinge, and a central hinge. Then the cable you can show like this. The cable has suspenders which are closely spaced. Let us do it very quickly. This is 100 meter. I call this as A, this is B, this is C. And there are two loads that are acting. One is acting at, it is mentioned in the question that the loads are acting at 20 meter and 40 meter. That means this is 50. I can take 20 meter here, one load acting, and another at 40 meter. I can take this another load at 40. So these loads are 10 kilonewton each. So this is 10 kilonewton. This is also 10 kilonewton. And then the cable has a central dip. You can see this is the cable. It has a central dip, that is this dip, which is equal to 10 meters. So this is the description that is given as far as the 3-hinged stiffening girder with supporting cable. The span is 100 meter. The loads are 10 kN, 10 kN. This is 20 meter. And this is 40 meter. I hope you are understanding the description of the problem. Now we have to analyze the girder, and then of course this is one suspender here you can add. So these are all suspenders which are very close to each other, and there is a cable. Cable is connected by means of suspender to the girder. Hope this problem is clear to you. Now let us analyze the girder and the cable. For that what we need is, we need to draw, I will just take out this, we need to draw the free body diagram of the cable separately and of the girder separately. But before that, let us find out the reactions. You know already, take moment about B equal to 0, that is, just write down. So VA into 100, I am taking moment about B equal to 0, VA into 100 for the girder minus 10 into 80, that is moment due to left load which is 10 kN at 20 meters from the left support, and then minus 10 into 60 is equal to 0. With that you are going to get VA is equal to 14 kN, and once VA is equal to 14 kN, total load is 20, you can write down sigma V equal to 0, then you will be seeing VB is equal to 20 minus 14, because total load is 10 and 10, that is 20, that is 6 kN. So the reactions of the girder are 14 and 6. Now let us draw the free body diagram of the girder first. You can see this is the girder. I will draw it a little bigger. Okay. So these are the reactions that we have found out. VA 14 kN, VB 6 kN, and then the two loads, of course this is point C, this is A, B. The two loads that are acting, one is at 20, another is at 40. So this is 10 kN, 10 kN. These are the two loads. They are acting at, already this is 20 meters, and this is 40 meters. Apart from this, which is very important is, now if you draw the free body diagram, the suspenders which are very close, they are subjected to tension. So the tension in the suspenders will be like this. Tension is what? It is the force which is acting away. So here also the tension is acting away. So this is the tension in the suspenders, and because they are very close, we can visualize or we can imagine that this is a UDL of W per unit length, which we do not know. We need to find out. You understand? Because the cable is acting like this. I will just draw. The beam is here. When you cut, you will see that the tension is always away. So that's what I have shown, the tension away from the girder, and this is W per unit length, and for this tension there will be reactions naturally. These reactions will be WL by 2 and WL by 2, this reaction. That means from the cable what we are getting is a UDL, that is through the suspenders, a UDL and the reactions which are acting, because UDL is acting upward now, so the reaction should act downward. So this is the free body diagram of girder. Now what we will do is, we will find out this W per unit length, which we do not know. For that what we need to do, we need to take moment at C equal to 0 with clockwise positive. When I take moment at C equal to 0, what are the forces that are acting? What are the forces that are contributing for the moment at C? That is VA, that is 14 into 50. Then moment due to 10 into 10, because this is 10 meters. Then moment due to this 10 into 30. Then moment due to UDL, that is clockwise. Then moment due to WL by 2. So that is what I have to write here. So I am going to write now the expression. So keep this in mind. First, VA into 50, that is 14 into 50 clockwise. Then moment due to this 10 minus 10 into 10. Then moment due to this 10 which is acting at a distance of 30 meters minus 10 into 30. Then moment due to UDL acting upward, so it is going to contribute for the positive moment, that is clockwise. So moment due to UDL is W into L by 2, that is L by 2 is how much? 50. W into 50 total load into 50 by 2. Then moment due to this WL by 2, and that is minus WL by 2 into 50, minus WL by 2 into 50. So you can see here moment due to 14 into 50 clockwise, moment due to 10 into 10 anti-clockwise, moment due to this 10 into 30 anti-clockwise, moment due to UDL clockwise, W into L by 2 into L by 4. Then moment due to this reaction which is acting downward, so it is creating anti-clockwise moment, minus WL by 2 into 50 is equal to 0. If you do the calculation, you will get W is equal to 0.24 kilonewton per meter, because W is the only unknown here. So operate your calculators, all of you, and check the answer. W is equal to 0.24 kilonewton per meter. Now after finding W, now what we will do is we will find out the bending moment and shear force at the point where it is at 30 meters. So I call that point as, you can see this is 20 meters, 30 meters. I call this as A, B, C, D. So let us find out bending moment at D and shear force at D. It's quite simple. Let us first find out shear force at D. What is shear force? Algebraic sum of all the vertical forces on the left of D. So it is plus 14 acting upward minus WL by 2, that is WL by 2. If you substitute W equal to 0.24, L equal to 100, you are going to get the value. Then moment due to WL by 2, then we will add minus 10, that is due to vertical load. Then shear force due to UDL only up to this point, up to the point of 30 meters, that is plus shear force acting upward, because UDL is acting upward, plus 0.24 into 30, and then shear force due to this reaction minus WL by 2. So this is the expression for shear force. You can see shear force at D point is equal to VA, that is upward, minus WL by 2. Of course this WL by 2 is written already here, so no need to write. Minus WL by 2, VA minus WL by 2, minus 10, then 0.24 into 30. That means how many components? 1, 2, 3, 4. So if you do the calculations, you will get the shear force is equal to minus 0.8 kilonewton. This is shear force at D point. Now similarly, we will find out now bending moment. Can I take care of this? I hope you have understood. So I will write down the bending moment. So let me quickly write down the bending moment. And you know what is bending moment at D? Bending moment at D is algebraic sum of all the moments on the left. That is, first is 14, that is 14 into 30. 14 is the vertical reaction here, into 30 clockwise, minus WL by 2 into 30, that is anti-clockwise. Then moment due to UDL plus W into 30 into 15 clockwise. Then moment due to 10 minus 10 into 10. So 4 components, 1, 2, 3, 4. You know already W, which is equal to 0.24 kilonewton per meter. L is 100 meter. You can substitute. You will get moment at D. I repeat again, what is moment at D? Algebraic sum of all the moments on the left side. VA into 30 clockwise. Then minus WL by 2 into 30 anti-clockwise at the point. Then minus 10 into 10 anti-clockwise. Then moment due to UDL plus, because UDL is acting upward, plus W into 30 into 15 is equal to the bending moment at D. And if you do the calculation, you will get 68 kilonewton meter. So this is bending moment at D. So we found out, we analyzed the entire girder. What we did first, we first found out the reactions 14 and 6 as it is by writing VA into 100 minus 10 into 80 minus 10 into 60 for the entire structure. We got VA 14 and VB 6. And after that, we wrote the free body diagram of the girder. What is this free body diagram of the girder? The girder has, loads which are acting, the reactions that are already there, 14 and 6, the low, and then the UDL, which is, obtained due to closely spaced suspenders. That UDL is W, we do not know, we found out afterwards. And then reactions due to UDL in the direction opposite to the UDL. UDL is acting upward, reaction is acting downward. So with this we found out the bending moment at D. Now the last item that is left out is the maximum tension in the cable. How to find out maximum tension in the cable? Now for that we have to draw the free body diagram of the cable. The free body diagram of the cable will be like this. You can see this is cable, and now the suspenders will be acting in the opposite direction, because again tension away, and then this is horizontal pull that we need to find out, and this is WL by 2, reverse WL by 2. This is horizontal pull, and this is 100 meter, and the central dip is 10 meter. Now how to find out horizontal pull? You know the formula. Horizontal pull is equal to, because this is symmetric cable, WL square by 8D, the formula what we had seen in the previous session. So substitute H is equal to WL square by 8D. You are going to get the horizontal pull, and the value of that will be 30 kilonewton. So when H is 30 kilonewton, then you can find out T max here or here, one and same. H is WL square by 8D. W we know already, 0.24. You can substitute. If you want, you can do that. 0.24 into 100 square upon 8 into 10. You will get 30 kilonewton. So H is 30 kilonewton. So T max, you know already, the resultant of these two, that is, which is equal to square root of VA square, not VA, WL by 2 the whole square, because VA is, we have given to some other, WL by 2 the whole square plus H square. So operate your calculator, you are going to get T max, and that will be 32.31 kilonewton. So these are the steps involved in the analysis of three-hinged stiffening girder. First, we analyze for the girder, find out bending moment and shear force at the point where we want to find out, and then we draw the free body diagram of the cable. Already we found out W, so we can find out WL by 2, WL by 2. Now keep this in mind that the suspenders, the tension will be acting, the UDL will be acting in the opposite direction. This is W per unit length, and the reactions are WL by 2 upward, the suspenders are acting downwards, horizontal pull away, T max. This is the formula that we had seen in the previous session. So we found out H 30 kilonewton, T max is this. I hope you have understood. If you have any queries, you can raise the doubts through your class representative, or you can directly contact me. Thank you.